Hello, everyone. So here we go, starting a brand new chapter, and that is chapter 7. Turns out that chapter 7 is taking us back a little bit to the atom itself. Now, we actually haven't closely examined atoms since, oh boy, chapter 2. And in chapter 2, let's just write that as a sidebar here. In chapter 2, we found out that the model of the atom that we currently use is the nuclear model. And in the nuclear model, we remember that, whoops, that should say model and not modette, right? So in the nuclear model, we found out that we had our positive protons and neutral neutrons in the tiny dense center nucleus of the atom, and the electrons were outside the nucleus. So let's just write that here, outside the nucleus. We found out other things, such as that the protons have positive charge, electrons equal but opposite negative charge, neutrons no charge, that protons and neutrons were the heavy subatomic particles in the nucleus, electrons much lighter. Well, our goal in this chapter is ultimately to take a closer look at these electrons, and to look at the properties of electrons and the actual location of electrons within the atom. In other words, we want to develop in this chapter a model that takes those electrons into account, far more so than just saying that they're not in the nucleus. Now, in order to do this, well, it turns out the place we have to begin is not with the atom at all, but is instead this topic here, which is electromagnetic radiation. And we study electromagnetic radiation first in this chapter because, as it turns out, it is from studies of how electromagnetic radiation interacts with atoms and ions that we are ultimately able to answer the question, all right, what are electrons doing in atoms? Where are they located? How are they organized? What are their properties? Okay, so having said that, let's jump in and start looking at electromagnetic radiation. Turns out that electromagnetic radiation is a phenomenon that can be described in one of two ways. One of those ways is right here. It's called the wave nature of light. Light is a generic term for electromagnetic radiation. And so we're going to take a look at how EM radiation, light, behaves like waves. But as it turns out, we're going to find out a bit later in this lecture that light can also behave like tiny particles. So both wave nature and particle nature of light are things we're going to explore. But let's begin at the beginning with the wave nature of light. And so I have here that electromagnetic radiation can be described as waves composed of perpendicular oscillating electric and magnetic fields propagating through space at 2.998 times 10 to the 8th meters per second. And you're like, oh my God, what is that? Well, let's start with that value here. It's a very important and famous value. And hopefully you all recognize that value as the speed of light. So let's write this down. Speed of light. That's how fast light travels. And this is typically given by the symbol lowercase c, speed of light. Okay. So electromagnetic radiation are oscillations in two fields that comprise our universe. Our universe is made up of electric and magnetic fields. These fields are at right angles to each other. And when these fields oscillate, we produce electromagnetic radiation. So over here, you can see that we have this oscillation, this blue oscillation, which is going up and down in the y direction. And this oscillation here is the electric field oscillation. Now, the magnetic field of our universe is at right angles to the electric field. And so this oscillation is going back and forth. It's coming out towards us in the z direction, and then it's going back in, all right, in the z, back into the plane of the paper, all right, out towards us, back away from us. It's in the z direction. And that is the magnetic field oscillation over here. And together, both of these oscillations comprise EM radiation. It's not electric radiation, it's not magnetic radiation, it's electromagnetic radiation because the two are a package deal. And well, these oscillations, these waves, are propagating along the x-axis here, at least in this figure. So I know the idea of fields oscillating, producing waves is a really hard thing to wrap your head around. So I'm going to make an analogy. Let's think about a pool, a swimming pool. That does sound nice, doesn't it? Okay, we could think of that pool as a field. It's a field of water. So it's a water field. Now, if we want to produce waves in that pool, in that field of water, what do we need to set up? Oscillations in the water. Now, how could we set up those oscillations? Well, you could jump in. If you jump in the water, all right, the water starts oscillating up and down. And now you have oscillations in your water field, which are water waves. Water waves. Well, instead of oscillations in a water field, we have oscillations in the electric and magnetic fields. Okay, so that was my little analogy before we go on. Now, if we just pull apart electromagnetic radiation, really what we're looking at, of course, is a waveform that is described by a classic sine function. So if you actually ever plot a sine function, you'll get what looks like a wave. And all waves, including electromagnetic waves, are primarily described by three characteristics: wavelength, frequency, and amplitude. The two that we're really interested in are wavelength and frequency, but we'll talk about amplitude as well. So when we look at the general shape of a wave, all right, the very top point of a wave is called a crest, while the very bottom point of a wave is called a trough. Crests and troughs. Now, the amplitude of a wave is simply described as the maximum displacement of the wave. So this is the maximum displacement of the wave. And we can measure the maximum displacement as either the vertical height of a crest or the vertical depth of the trough. So it's either the height of crest, or we could also measure it by calling it the depth of a trough. In other words, this distance here. I'm drawing a little dotted line because my hand is always very shaky when I draw straight lines. And I'm not doing a great job with dotted lines here. So this here would be the amplitude of a wave. Amplitude. Okay. Amplitude is indicative of how bright or how intense the radiation is. So a bigger amplitude means a brighter or more intense radiation, whereas a smaller amplitude indicates a dimmer or a less intense radiation. So I'm also going to note that this indicates the brightness, or another way to say brightness is intensity. Brightness or intensity of the radiation is what it correlates to physically. Okay, well that's amplitude. Well, let's go to wavelength next. So I'm going to scroll up, down. I'm not sure which way you would say I'm going. So what about wavelength? Well, wavelength is something you have met before. Wavelength is most often described as the distance between any two successive points along the wave. So this is the distance between any two repeating successive points along the wave. Okay, so for example, what color should I do wavelength in? Let's do it in purple because purple is fun. Okay, so for example, this point here, which is at the top of the crest, repeats itself right here at the repeating crest. That means that this distance here is the wavelength of the wave. But it's the distance between any two repeating points. And so if I could take this trough here, and this trough repeats itself right here, well, this distance is the wavelength of the wave. And they're both the same distances, so crest to crest, trough to trough, but it doesn't have to be crest to crest or trough to trough. It could be any repeating point. So let's take this point right here. This point then repeats itself right over here. And this distance is the same as the other two that I've done in purple. This is the wavelength of the wave. So any two repeating points. And the wavelength indicates what I would describe as a complete cycle or a complete oscillation. So for example, when we're starting at the top up here, all right, we're going down and then back up. So the down up is a complete cycle. So let's note that this represents a complete, let me change my color here. All right, so represents a complete cycle or a complete oscillation. Now, since wavelength is so important, we are going to designate it with a symbol, and the symbol we use for wavelength is the Greek letter lambda. So this is lambda, and this is lambda. Not very good lambdas, but you get the idea. So lambda is the symbol that we use for wavelength. And what about the units that we use for wavelength? Well, wavelength is a length. It's a distance. And so the SI unit is the SI unit for distance, which is the meter. It's the meter. And of course, we can put all sorts of prefixes in front of the meter. We can have wavelengths in kilometers or picometers or micrometers, etc., etc. Okay, so there we have wavelength. Well, that's going to take us to the next important characteristic, and that is frequency. And as it turns out, the frequency of a wave is defined as the number of cycles or the number of waves that pass a given point in space each second. So let's write that here. This is the number of waves or, complete cycles that pass a given point in space, each second. Okay, so there's our definition of frequency. Okay, so let's suppose you are a surfer and you paddle out onto the ocean, and every time a water wave passes you by, all right, as you sit there on the ocean, so that's the point in space where you are floating in the ocean, every time a wave passes you by, you go up, down, all right, you bob up and down. Okay. And well, as you sit out there, and if you're not actually interested in surfing and you just want to float around, well, you could count and say, well, how many waves are going by me? Maybe not each second, but each minute, or every 10 minutes, or every hour, and you would have the number of waves going by you in a particular unit of time. Well, the unit of time for the frequency of electromagnetic waves is per second. So we're counting waves that flow by per second. Now, as it turns out, the unit for frequency, let's get another color here. Let's go with red over here, is kind of a curly U, and I didn't do a very good job here. All right, the symbol is called nu. And nu looks like a cross between a U and a V, and it's kind of curly. And this is the symbol over here. This is the symbol, nu. And the SI unit that is used for frequency, well, the SI unit comes from the description of frequency. It's the number of cycles that pass a given point in space each second. So you might think it is cycles per second. And you'd be sort of right. It's not cycles per second because, well, it's considered redundant to put the cycles in. It's like, well, of course we're counting wave cycles. What else would we be counting? We're not counting cars. We're not counting balls. We're counting cycles. So we take the cycle out, and that leaves the SI unit as 1 over seconds, or you could write it as seconds to the negative 1. We call this per seconds or inverse seconds. Now, it turns out there is another unit that is used for frequency in place of per seconds, and that is the hertz. Hertz, which is abbreviated Hz, as it turns out, 1 hertz is identical to 1 per second. So they're the same unit. So this is renamed the hertz because that's what we often do when we have derived units. We get to rename them, usually by using names of people who studied those phenomena. Now, an important relationship that I should mention between wavelength and frequency is that they are inversely related. So I'm going to note here that wavelength and frequency are inversely proportional. Inversely proportional. Okay, so let's put a little star beside that. So what does that actually mean from a practical perspective? Well, it means that when frequency goes down, wavelength goes up, and vice versa. Here, I'm going to do that the other way around because I would like to match it to my pictures. So when frequency goes up, wavelength goes down. And, well, if we're going to describe the resulting wave that we get, this means that the wave is going to have high frequency. And, well, when wavelength goes down, we have short wavelengths. And that gives us a wave that looks like the blue wave, high frequency and short wavelengths. On the other hand, when frequency goes down, wavelength goes up for our inverse proportionality, and that means waves with low frequencies have long wavelengths. And that's what we get with the red picture over here. Long wavelengths, all right, with low frequencies. Okay. Now, it turns out the actual mathematical relationship between wavelength and frequency is something you studied in Chem 10. All right, turns out, well, all electromagnetic waves propagate at the speed of light, which we've already seen is c over here, 2.998 times 10 to the 8th meters per second. And as it turns out, the equation that binds frequency and wavelength together, all right, is, well, the term that's going to bind them together is the speed of light. And that equation you should recognize is c equals lambda times nu. And we are going to circle and star this as our first important equation. Sometimes this is just referred to as the speed of light equation. I'm not sure that it's its technical name. The speed of light, c, is a constant. And so now we can see when one of these terms goes up, the other has to go down. That's why they're inversely correlated. Now, since the units of the speed of light are in meters per second, when you use this equation, wavelength has to be in meters and frequency has to be in per seconds, because meters times per second give us what? Oh, they give us meters per second up here. So you do have to watch out with units. Now, how is this equation used? Well, it's essentially used as a conversion relationship. If you know frequency, you can get wavelength. If you know wavelength, you can get frequency using this really basic equation. So let's take a look at a couple of practice problems, some ice problems from Chapter 7. And the first problem I have here says that hard X-rays are commonly used for diagnostic radiography. All right, that essentially means that when you break a bone, you're going to be using hard X-rays to, all right, take a look at the break and make a diagnosis. It says here to calculate the frequency of hard X-rays with a wavelength of 63 p.m. Now, it's been a long time since you had to study your metric prefixes. This is the time where you're going to have to reacquaint yourself with those metric prefixes because they're going to come back with a vengeance right now. You got to know all of them. So what we have here is a wavelength of 63 picometers. Pico is 10 to the negative 12. So this is 63 times 10 to the negative 12 meters, or 6.3 times 10 to the negative 11 meters if I write this in scientific notation. Now our goal is to get frequency. So how are we going to do that? Well, we have this handy dandy equation, C equals lambda times nu. So what do we want? We want nu. I know, it's silly. Might as well be silly. And we know these two values, so it's just a plug and chug and a rearrangement. So nu over here is equal to C over lambda. And note that I already have lambda, which is wavelength, in the correct units in meters. So we're going to get 2.998 times 10 to the 8th meters per second for the speed of light. We're going to divide this by 6.3 times 10 to the negative 11 meters. And if we look closely at those units, meters cancel meters, which means our final answer is going to be in not seconds, but in per seconds. Always be careful and watch out for that. Looks like my final answer is going to be in 2 sig figs. And to 2 sig figs and in scientific notation, because you also need to put things in scientific notation, I get 4.8 times 10 to the 18 per seconds, which I could also write as 4.8 times 10 to the 18 hertz as my final answer here. Let's put a box around it. So you want to also be careful with your math, because not only in this chapter are those prefixes going to be important, but doing calculations with scientific notation, very large, very small values, is also going to become really important in this chapter. Okay, moving on to the next example here. Number 2 of our in-class example says a radio station broadcasts at 89.9 MHz. What's that stand for? Megahertz. We're asked to calculate the wavelength of this broadcast. So megahertz, hertz, is a measurement of frequency. And so that value we have here, 89.9 megahertz, is the frequency. Okay, well, mega is 10 to the 6th. So this is 89.9 times 10 to the 6 hertz, which is, if I write this in scientific notation, 8.99 times 10 to the 7 hertz. Now, while hertz are all well and good, it's really going to be difficult for you to see how units cancel out. And so I'm going to replace hertz with per seconds. That way you'll see how units cancel out perfectly. Now, we have frequency. Our goal is to figure out the wavelength of this broadcast. So once again, we're turning to the speed of light equation, C equals lambda nu, but this time we want lambda. And that's because we have nu and C that we can just plug and chug and solve for this. So rearranging my equation, lambda equals C over nu. And here we go again, 2.998 times 10 to the 8th meters per second divided by 8.99 times 10 to the 7, and this is in per seconds. And now you can see why I wanted to put the frequency in per seconds, because the per seconds here cancel with the per seconds here. And what units are we left with? Meters for our wavelength. And looks like we are going to need 3 sig figs. As it turns out, my final answer here is 3.33 meters. Wow, those are pretty long waves. The wavelength of radio waves, 3.33 meters. That's like 2.5 of you put together. Maybe not 2 of you, but yeah, about 2.5 would be 3.33 meters. Compare that to the X-rays in the previous problem. The X-rays had a wavelength of 63 picometers, while our radio waves 3 meters. That's a huge difference. And that's because, well, all right, they're very different types of EM radiation. And so the next thing we're going to take a look at right here is the electromagnetic spectrum. So the electromagnetic spectrum takes all of the major types of EM radiation and organizes them by their frequency or by their wavelength. And let's take a look at the figure below. So the major types of EM radiation are written in this table. We have radio waves, microwaves, infrared. Then this little tiny band here, which is visible light, and it's sort of blown up because it's so tiny in this picture, followed by ultraviolet radiation, X-rays, and gamma rays. I should note that infrared is often abbreviated IR, and ultraviolet is often abbreviated UV. Visible light is often abbreviated just with VIS. And they're going to be becoming more of the important types of radiation as we move along in this chapter. Well, it turns out as we go from left to right across this list of types of radiation, it's actually a list in order of decreasing frequency. So in this list, all right, we have high frequency, sorry, it's increasing frequency, it's decreasing wavelengths, my bad. So it turns out we have low frequency radiation on this end. So radio waves, low frequency, but as we go from left to right, all right, gamma rays on the other end are high frequency radiation. Now, because wavelength and frequency are inversely proportional, that means if radio waves on the left side have low frequencies, they must have long wavelengths. And as we go from left to right, long wavelengths are getting shorter and shorter and shorter. So on this end, we have the shortest wavelengths. So radio waves, long wavelengths, gamma rays, short wavelengths. So what we have here is increasing frequency, going from left to right. That should be an increasing frequency. And we have decreasing wavelength, going from left to right. And you can see this in this picture of a wave. All right, radio waves over here with very long wavelengths. And as we go from left to right, we can see what's happening to the wavelengths. It's getting smaller and smaller and smaller until we get to our gamma rays at the far end. So what kinds of wavelengths do these different types of radiation have anyway? Well, radio waves don't have one wavelength, or microwaves. They have a range of wavelengths. But if we were going to look at what typical wavelengths would be for these different types of radiations, well, radio waves typically have wavelengths that are on the kilometer or meter scale. And we see that in the radio station broadcasted number 2 over here. We ended up with 3.33 meters. So kilometers, meters are fairly normal for radio waves. Meanwhile, microwaves, that's a little bit misleading. You might think microwaves are, all right, micrometers, but they're not. All right, microwaves are typically in the centimeter range of wavelengths and maybe down to millimeters. Microwaves, centimeters and millimeters. Meanwhile, infrared tends to occur in the millimeter and the micrometer range. That's a micro with a funny M. Okay. Now, visible light is rather interesting. Visible light occurs in the hundreds of nanometers. As it turns out, visible light ranges from 400 to 700 nanometers, where red at one end of the spectrum is 700 nanometers, and at the other end of visible light, we have 400 nanometers, and that's the range for visible light. Okay. Well, ultraviolet light also tends to have wavelengths in the nanometers, just nanometers less than 400 nanometers. X-rays tend to be in the picometer range, whereas gamma rays tend to be in the picometer and even femtometer range. So you can see how these wavelengths are getting smaller and smaller and smaller. Okay, this table only shows the major types of EM radiation, but there are other types of EM radiation, and we can also subdivide the types that we see here into more specific classes. So for example, these radio waves here, well, radio waves include FM radio and AM radio. They also include TV waves, Yes, TV does get transmitted in waves, especially if you have an older TV or you've cut the cord of the cable and you've gotten yourself a pair of rabbit ears. Those rabbit ears are picking up TV waves. So, yes, radio waves. Um, in between radio waves and microwaves, sort of halfway in between them, you have radiation such as the radiation used in remote controls, whether it's a remote control signal that's used to open your garage door or turn on your TV. Um, Another type of radiation you find in this region here is the radiation for your cell phones, which is kind of interesting. Okay, so like I said, these are the major categories, but all right, they're little hidden categories as well. Now, I do want to talk a little bit about visible light. Visible light, of course, is, well, light we can see. And by we, I mean us humans. It is EM radiation visible to the human eye based on evolution. And ultimately, we can take visible light and split it into, well, it can be split into component colors, either by passing that light through a prism or diffracting it off of something called a diffraction grating. Sometimes visible light is called white light because that's how it often appears. So if we take some visible white light and we take that visible white light and direct it towards a prism, well, that light will get refracted through the prism. We could also use a diffraction grating. An example of a diffraction grating is a surface that has very fine grooves etched into it. And well, for an everyday example, think of the surface of a CD or a DVD. They have very fine grooves in them, and when light bounces off of those grooves, it splits apart. And what does it split into? Well, it splits into a classic rainbow. Except because we're, smart people, we don't call it a rainbow. The technical term for a rainbow is a continuous color spectrum. That's not how you spell continuous. Let's try that again. Continuous color spectrum is what we end up with here, aka a rainbow, where all of the colors are represented, as you can see here, red, orange, yellow, green, blue, and violet. Where red, all right, is 700 nanometers at one end, and at the other end of the spectrum, violet light with a wavelength of 400 nanometers, and the other colors having wavelengths falling in between. So I'm going to give myself a little room here. Note that when we go from red to violet, what's happening here is that wavelength is doing what? Wavelength decreases. And if wavelength is decreasing, what's happening to frequency? It means that frequency is doing the opposite. Frequency is increasing. So wavelength decreases, frequency increases in our continuous color spectrum. By the way, why is it called a continuous color spectrum? Well, when we look at a rainbow, all right, we can identify the part that's red, but can you point to a rainbow and say, this is the point where red becomes orange? You can't do that, all right, because of the very minuscule gradual changes in color. You can't point to that exact moment when red becomes orange, orange becomes yellow, yellow becomes green. It's a smooth, continuous transition from one color to the next. So as we can see, each color in visible light corresponds to a different wavelength and a different frequency. Now, all right, if you go to wavelengths above 700 nanometers, well, can you see this light? Well, it depends on how good your eyes are. Some people can see maybe 720 nanometers, a little bit further up, but most people usually, all right, can't see much beyond 700 nanometers. And that's because we're not in the visible light region anymore. So what's past red? Well, infrared is past red. So red is bounded by infrared, and infrared will have wavelengths greater than 700 nanometers. Meanwhile, at the other end, Whoops, let's push this up, but choops. Okay, if we go to wavelengths less than 400 nanometers, again, very difficult to see any wavelengths with our eyes less than 400 nanometers. We're no longer in visible light. We're now in ultraviolet. So violet is bounded by ultraviolet. Red is bounded by infrared. Now, you do need to know not what the actual wavelengths are of these types of radiation, but which have higher and which have lower frequencies, which have longer and which have shorter wavelengths. So, for example, you need to know, for example, that red light has a longer wavelength than, say, X-rays, which have shorter wavelengths. You need to know that microwaves have lower frequencies than violet light, for example. So you need to know the relative differences here in their frequency and wavelength of all of the major categories of EM radiation. Okay, so we've talked a lot about light and how it behaves as a wave. Do we have any actual evidence of how light behaves as a wave? All right, how do we know that light is wave-like? Well, we compare the behavior of light to other known wave phenomena, like water waves or sound waves. What are the characteristic behaviors of water waves and sound waves? And, well, we see, wow, check it out. Light behaves a lot like water waves and a lot like sound waves. So what sorts of things does light do that other types of wave phenomena do? Well, we see things like light reflects, it refracts, and it diffracts. Now, I'm not going to teach you what these things are. All right, you'd have to take a physics course to learn this, and this is not a physics course, so you'll just have to take my word for it. So I'm going to say EM radiation, all right, reflects, refracts, and diffracts. Okay. Other thing that EM radiation does are things like um, undergoes constructive and destructive interference and ultimately can form things called diffraction patterns, which we also see for other known wave behaviors, like I said, water waves, sound waves as an example. So undergoes constructive and destructive interference, forming something called diffraction patterns. And I'll also note that something else we see that light does that other types of all of the other types of waves do is it obeys the it exhibits something called the Doppler effect, which you may have heard of. So exhibits the Doppler effect. And again, this is not a physics course. If you've taken physics, you'll recognize a lot of these things. If not, don't worry about it. But these are all verifiable wave behaviors that we see light engaging in, that we see EM radiation participating in. Okay, so we've described light, EM radiation, all right, as being wave-like. But it turns out EM radiation can also be described using a particle model. And so the next thing we're going to take a look at is how to describe light as not waves, but as particles. So let's move this up here. Turns out that in the late 1800s, the accepted view of light was waves. Waves were the prevailing view. Light exists as these undulating oscillations, as these waves. But eventually we ran into some problems. And one of the first problems was understanding a phenomenon known as black body radiation, where black body radiation is the radiation emitted by solids heated to incandescence. So this was a well-known phenomenon. For example, if you take a piece of metal, and that's shown in this picture here, and you start to heat up the metal, you start to raise its temperature. as you raise its temperature, eventually that very, very high temperature metal starts to glow. And that glow is radiation being emitted. And that's what blackbody radiation. It's the glow that's emitted by very, very high temperature solids. And well, the color of the glow changes based on its temperature. So let's just note over here. So this is for blackbody radiation. Black body radiation. All right. So I'm going to say glowing metals at high temperatures are a good example of black body radiation. And like I said, the color of the glow changes as temperature gets higher and higher. So at around 1,000, let me see if that number is correct. Somewhere I have notes that I should be looking at here, but not surprisingly, I lose my notes. 1,000 is a little bit high. At around 700 degrees Celsius, okay, the glow of a heated metal is sort of red or reddish glow. As you keep raising the temperature, say to about 1,000 degrees Celsius, the glow shifts from red to a kind of orange-yellow color. And if you keep raising the temperature, maybe to about 1,500 degrees Celsius, the glow changes to white. Most of you have heard of the expression red hot and white hot. And of course, everybody knows white hot is a lot hotter than red hot. And well, you can see it right here. Now, I'm not going to talk any more about blackbody radiation, except to say that it was well studied and a lot of experimental results were obtained from the studies of blackbody radiation, but the prevailing theories of the time could not explain the results. So the theories said one thing, but the experimental results said another thing. That drove the scientists crazy, right? So as it turns out, blackbody radiation is finally going to be explained by a German scientist named Max Planck in 1900. And to explain blackbody radiation, he ultimately comes up with the idea that matter can only absorb or emit energy in tiny discrete packets called quanta. And the singular of quanta is quantum. And he is able to determine the amount of energy that matter can absorb or release, all right, with an equation that's named after him. And that equation is delta E equals N H nu. And I'm going to circle this equation and start. And this is named after him. It's Planck's equation. Okay. So what are the terms in this equation all about, and what does this equation ultimately tell us? Well, delta E is the energy change of the system when it either absorbs or emits energy. So this is the energy change of the system when it absorbs or emits EM radiation. Now, n over here is simply a whole number integer that can take on values 1, 2, 3, 4 to infinity and beyond. Now, we are absorbing or emitting EM radiation, and so nu in this equation, all right, refers to the frequency of the emitted or absorbed radiation. So this is the frequency of the absorbed or emitted electromagnetic radiation. Which takes us to the last term in this equation, which is H. H is a new constant, and it's named after Planck. It's called Planck's constant. And Planck's constant is given a value of 6.626 times 10 to the negative 34, really tiny number in units of joules times seconds. We call that joule seconds. Now, that's a very, very, very small value, which means when you take that very small value of Planck's constant, multiply it by a whole number, multiply that by the frequency of the EM radiation, what are you going to get? You're going to get a really small number. So the product of N, H, and nu is a very small number. And that very small number represents the tiny discrete packets of energy that matter is absorbing or emitting. In other words, matter cannot absorb or emit energy continuously as a flow. All right? It has to absorb or emit energy in chunks, little chunks. It takes on a chunk of energy and another chunk of energy and another chunk of energy. And every one of those chunks is a really, really tiny chunk of energy. So this quantity here, all right, right here, is going to be a very small value. And this quantity here represents these tiny, discrete chunks or packets, and they're called quanta. Okay, so that's the first step. Now, later on, Albert Einstein himself is going to study another phenomena known as the photoelectric effect. And we're going to look at the photoelectric effect in detail in the next lecture. And when he studies the photoelectric effect, which no one is able to explain, he realizes that it can be explained if light itself is also quantized. In other words, instead of thinking of light as continuous waves, instead we should be thinking about light as chunks or packets of EM radiation. And this is exactly what he suggests, is that EM radiation, that light is really packets, chunks of EM radiation, and he calls these chunks of EM radiation photons. Where, as it turns out, the energy of these chunks of radiation, all right, can also be expressed using Planck's equation in a slightly modified form. And the modified form of Planck's equation that is used to calculate the energy of these light chunks, these light particles, is the following, that E photon equals H times nu. And I'm going to circle this equation here, which is just a modified version of Planck's equation. It's still called Planck's equation. And it turns out there's an alternate version. If we recall that nu is equal to C over lambda, we can then replace nu in Planck's equation with C over lambda. And what do we end up getting? Well, we'll get that E photon is equal to H times C over lambda, if I do that very simple substitution. So I'm going to circle this as well. And it doesn't matter which one you use, they're both Planck's equation. Planck's equation, Planck's equation. Planck's equation is what we have here. Okay? Where once again, H in these equations is Planck's constant, which we already have up there. In the second form, C is the speed of light. And well, nu or lambda are either the wavelength or frequency of the radiation. So let's note H is Planck's constant. And over here, nu is the frequency of the EM radiation. And over here, lambda is the wavelength of the EM radiation. And as it turns out, we always stick with SI units. Turns out that the frequency of the radiation is always in, per seconds. Planck's constant we've seen is joule seconds. And if I multiply joule seconds by per seconds, what cancels out? Well, the seconds do. And so E photon in both of these will be calculated in joules. We'll get that in joules. So this is another chapter that's big on SI units. Now, let's note something important here, and that is the relationship between frequency and photon energy and wavelength and photon energy. So let's note from the first form of Planck's equation that frequency and photon energy are directly proportional. In other words, over here, as frequency gets bigger, energy also has to get bigger. So that's a direct proportionality. So frequency and E photon are directly proportional. In other words, frequency goes up, E photon goes up. However, when we look at the other form of the equation and look at the relationship between wavelength, which is right here, and E photon, well, that's an inverse relationship since wavelength is in the denominator. And so I'm going to note that wavelength and E photon are inversely proportional. So let's get this here, inversely proportional, which means when wavelengths get long, photon energy gets low. So with this information, I actually want to go back to the EM spectrum that we have earlier in your notes. So I'm going to pull this back over here. So let's note that the information in the EM spectrum here is from low wavelengths, low frequencies, long wavelengths, increasing frequencies, decreasing wavelengths to the other end to high frequencies and short wavelengths. Well, we can also see that this tells us something about the energy of the photons of different types of radiation. If the radiation has low frequencies and long wavelengths, this means that we have low photon energy. And at the other end, we're going to have high photon energy. So increasing frequency, decreasing wavelength, and this is also in order of increasing photon energy. In other words, radio waves with low frequencies and long wavelengths, if we think of them as photons, as chunks or packets of energy, well, those packets don't have a whole lot of energy. They have low photon energy. But gamma rays at the other end with high frequencies and short wavelengths, femtometer wavelengths, well, the photons of gamma rays carry a lot of energy, high energy photons for the gamma rays. So let's go back over here where we sum it up. So as it turns out, we can describe electromagnetic radiation ultimately in two ways. And one of those waves is waves. Waves that are smooth and undulating. Or we can describe electromagnetic radiation as a stream of photons traveling through space at the speed of light. Now, can I draw a photon? No. A photon is an energy particle. But I suppose if I did, there we go. All right, little separate photons, like, I don't know if you're tricky, photon torpedoes, right? Okay, all right, but each photon is discrete and separate from the next. Unlike waves, waves are not separate. Waves are undulating and continuous and forever, but both descriptions of EM radiation are perfectly correct. Okay, so let's do a couple of examples and end this lecture. So number 3 on our ICE handout says a gamma ray photon emitted by radioactive cobalt-60. That's an isotope of cobalt-60. All right, has an energy of 1.33 MeV. MeV stands for mega electron volts. 1 electron volt, 1.602 times 10 to the negative 19 joules. We're asked to calculate the frequency of the emitted radiation. Okay, so you can imagine a cobalt-60 isotope doing what? radiating gamma rays, killing everybody with those horribly high energy gamma rays, turning them into the Hulk. Well, no, that would be interesting if that happened. And well, what do we know about the gamma rays being emitted by this radioactive isotope? We know their energy. So we've got E photon. E photon equals 1.33 MeV. Now, we don't particularly like mega electron volts, so we know that there are 10 to the 6 electron volts for every one big mega electron volt. But we also know we like to work in SI units of joules, so times 1.602 times 10 to the negative 19 joules for every 1 electron volt. So megas cancel megas. That should be 1 down here. And then electron volts cancel electron volts. And we're now going to have the units of the energy of that gamma ray photon now in units of joules. And as it turns out in joules, I get 2.13 times 10 to the negative 13 joules. Now, we'd like to know the frequency of the emitted radiation. Well, we know that E photon is given by the formula H times nu. And what do we want? We want nu. We want the frequency of the radiation. Well, we know E photon. All right, H is Planck's constant, so it never changes. So rearranging, the frequency of this radiation is going to be E photon divided by Planck's constant, or 2.13 times 10 to the negative 13 joules divided by Planck's constant, 6.626 times 10 to the negative 34 joule seconds. So what's going to happen with our units? Joules cancel with joules. What units are we left with? Be careful. We're not getting seconds. We're getting per seconds. And so plugging and chugging this out, looks like we're going to reduce to 3 sig figs in scientific notation. I got 3.21 times 10 to the 20 per seconds, which you could also write as 3.21 times 10 to the 20 hertz. So there we have that. Okay, let's do one more here and then close out this lecture. I know it was a long one. So number 4 says, when heated, a sample of copper emits blue light with a wavelength of 451 nanometers. So imagine, if you will, a piece of copper that, I don't know, we heat up in a Bunsen burner flame. And what happens to the copper? It's glowing blue. Blue light is being given off by our hot copper. And what do we know? Well, we know the wavelength of the emitted radiation. So blue light, of course, is EM radiation, and the wavelength is 451 nanometers, which is 451 times 10 to the nano is negative 9 meters. Or if I write this in scientific notation, 4.51 times 10 to the negative 7 meters. Now, our goal is to calculate first the energy of one photon of this radiation, as well as the energy of a mole of photons. Now, we have 2 equations that can be used for Planck's equation. One of them is E photon equals h nu, or we could use E photon equals hc over lambda. Well, in this problem, we're given lambda. Okay, so we might as well use this form of the equation, because it's allowing us to calculate the energy of the photon directly using wavelength. Okay, so plugging and chugging that out, we're going to get that E photon equals H, which is Planck's constant, 6.626 times 10. You know what? I don't have quite enough space here, so I'm going to give myself a little more room. Here we go. E photon equals H 6.626 times 10 to the negative 34, units are joule seconds, times the speed of light, c, 2.998 times 10 to the 8th meters per second, and we're going to divide by our wavelength in meters. We always use SI units. 4.51 times 10 to the negative 7 meters. Looking at our units, seconds cancel the per seconds. Meters cancel the meters. We're left with our photon energy in joules. And in joules, I ended up getting a value of 4.09 times 10 to the negative 19 joules. I'm going to put my little box around this answer here. Is that a lot of energy? Well, no. 10 to the negative 19 joules is a very, very tiny amount of energy. But that's because this is the energy carried by one photon. So one teeny tiny photon only has a teeny tiny amount of energy. All right, it's a quantized, discrete, tiny, tiny packet of energy. Kind of like the way an atom, one atom by itself, has a teeny tiny mass. So it's sort of an analogy there. All right, so tiny energy of one tiny photon. One tiny photon of blue visible light. Okay, so that's part A. Part A wanted us to get the energy of a single photon, and that's what we have here, the energy of one photon. Now, when I'm working with atoms, when we do any sort of chemistry or calculations, we don't work with just one atom. One atom has too small of a mass. We can't pick it up. We can't weigh it. And so we always scale up. And what kind of quantities do we scale up to? Mole quantities. Well, we do the same thing with photons. We can scale up our photons from individual photons to moles of photons. And so in part B, we are now asked to calculate the energy of a mole of photons in kilojoules per mole of this same radiation. So, well, this is going to involve Avogadro's number. So in part B, we're going to start with what we have, which is 4.09 times 10 to the negative 19 joules. Well, this is the energy per one photon, so let's think of this as joules per photon, where every photon of this blue light has this amount of energy. But we want this in kilojoules, so to convert to kilojoules, 1 kilojoule per 10 to the 3 joules, and so goodbye joules. But we don't want it in kilojoules per photon, we want it in kilojoules per mole of photons. Well, I know that 1 mole of photons must be 6.022 times 10 to the 23 photons. So 6.022 times 10 to the 23 photons for every 1 mole of photons. And so now we cancel out photons, and what's left? Well, now we have our energy in kilojoules per mole. And plugging and chugging this out, I ended up getting a value of 246 kilojoules per mole, which looks like a very respectable macroscopic quantity of energy. So just as scaling up to mole quantities of atoms gives us measurable quantities of atoms on a scale, well, scaling up the number of photons to mole quantities gives us measurable amounts of energy. Okay, now the last thing I want to mention is well, what evidence do we have that light, that EM radiation can behave as these particles, these photons? All right, they are photons, they're particles of light. And well, the answer is, well, the experimental data that Einstein was analyzing, and that is the photoelectric effect. Serves as one of the most important bits of experimental evidence that light can behave as photons, and that is going to be the subject of our next lecture. So until then, all right, I will be talking to you soon, and take care. Bye now.